My name's Ed Southall, and I'm going to be talking to you a bit about the words of mathematics and their origins, and how they're constructed, which will hopefully make a few things make a bit more sense, because a lot of the words are quite foreign, really. They feel like a different language, and I think it's probably wise to think of them that way. And most of the words we use aren't really used outside of mathematics very much. So for a child, it's no surprise that when we start using this terminology, they get a little bit lost. So I'm going to show you the main sources for what I used for this presentation. So these are the, I've used a few other things as well, but these are the main sources. We've got 3 books here. The first one's called The Words of Mathematics, and that's available from the MAA. You can only get it as a PDF now, unless you're quite lucky on eBay or something. I think that was written in 92 or 93, so it's quite old now. But it's a great book, really nicely written, and really, really informative. And I've picked a few things out of there that I've really liked. The second book is very similar to the first in terms of its content. It's essentially just a dictionary of maths and explaining the etymology of some of the words. And it's more recent, but what's hilarious with that book is the author, Anthony Lobello, is just the most cynical, mean human being I think I've ever got the impression of just through page alone. So his book is quite amusing to read, and I'll give you a sample in a second to get a feel for the sort of tone of the way he writes. And the last one is a lovely book called Enlightening Symbols by Joseph Mazur. Again, really, really informative. So if you are interested in this stuff, if there's more you want to learn about etymology and the origin of symbols and things like that in maths, then I would strongly recommend those 3 books as a kind of launch pad. They're all academics as well, so they've got papers and journals and stuff alongside this stuff that you can look at in your own time. So I'm just going to give you a quick sample of the book by Anthony Lobello, so you can get a real feel for what I'm talking about, because I just think it's worth sharing. We often talk about how academics in maths, myself included, some of them have distinct personalities, let's say. Well, I think this guy's personality shines through in the style of his writing. So I've got two samples here, which I think highlight that quite nicely, or if nicely is the right word. So the first one here, we have infinitesimal, and for his definition of this, he begins by saying, this is a very strange world, which is, I think, probably the politest he is throughout the whole book. But then if you look at the bottom of that segment, poor Dr. Johnson, who I don't think gets mentioned anywhere else or explained away, but clearly the author knows him, and maybe he knows the author. Dr. Johnson suggests something that makes no sense at all. So that's his summation of him. And then he includes in these books some slightly random choices, like MacLeod here, and he puts PowerPoint in just to have a rant about PowerPoint, which is brilliant. But MacLeod obviously causes him a little bit of anger. It's something defined by the illiterate, apparently. So there we go. And in fact, don't worry, I won't go on about him for too long, but he's well aware of the other book that I mentioned, Schwartzman's book. So when he's talking about the word monoid here, he mentions Schwartzman specifically, and is a little bit dismissive about him as well. Now that is slightly relevant to this presentation, because some of the roots of some of the words that we're going to talk about are sort of debated, particularly the narratives behind some of the sort of mistranslations and things. So do keep in mind that I've gone with what the majority tend to say about some of these words, but they are up for a little bit of debate. Anyway, let's crack on. So this is called From Abacus to Zero, just because abacus is a word that begins with A and zero is a word that begins with Z. I've tried to kind of structure it alphabetically, just because it's a bit easier for me. So we will start with the word abacus. Abacus, hopefully you can appreciate, is a really weird word. It sounds odd. Anyone who's followed me for a while might recall that I've got a bit of a bugbear about abaci or abacuses or whatever the plural is, just because there's lots of different types, and the least useful type of abacus is the one that the UK seems to have adopted as a counting tool for children. There's much better ones that can be used for mathematical purposes, but I digress. So abacus, the word itself, has a couple of definitions. I mean, we're all used to the mathematical definition, but it also means the flap, slab, supporting, and architrave. So if you are an architect or you live with an architect, you may have used this word or heard of this word being used in a different context. But for us, really, we know it to mean one of these devices with little beads that you thread along and so on. Lots of different manifestations of the abacus. There's Russian abacus, Chinese abacus, our stupid abacus, and so on. But the word itself is pretty weird. But it has its purpose, it has its roots, and those roots make sense, as with pretty much every word in mathematics. So this one has a kind of a crossbreed meaning in some ways. You've got abax, which is Greek, meaning a slab, and you've got abak, which is Hebrew, meaning dust. So between the two, you're probably none the wiser as to why it's using those words in that sort of translation of how we see it and use it today. But it's essentially linked to the tools that were used way back when to do mathematics. So if we just have a look here, we've got slab and dust. If you've watched any of the old any films that depict famous mathematicians doing maths in the old days, like Hypatia and so on, you'll see that they are doing maths in sand. They have a slab, they cover it in sand or dust, I suppose, but it's usually thought of as sand, and they would draw on that sand with sticks. And use pebbles to indicate different sizes of quantities and things, and it comes from that. It comes from that sort of idea. So there is purpose behind the words. It's not just a random thing that's been thought up. If you haven't seen the film Hypatia, it's pretty good. So this is a scene from it where you can see that she's kind of doing that sort of thing. It's astronomy essentially, but she's doing maths in the sand, if you like. So that's our first word. I'm going to leave it at that for that. Next word is algebra. So again, a really strange word to use. Doesn't get really used anywhere else outside of maths. And algebra is actually the name of a book. Algebra, like this, AL space JABR, and this is Arabic. And this book was written by a mathematician called Muhammad ibn Musa al-Khwarizmi. I'm sure I haven't quite pronounced that right, so forgive me. And you may notice that with his family name, al-Khwarizmi, that does sound a little bit like another word that we use, algorithm. And in fact, algorithm is a derivation of that name. So Algebra means the reunion of broken parts. And this was a book that sort of formally introduced to a wide-ish audience some of the notions of algebra as we know it today, hence why those ideas were collectively named after his book. And he's a great link for teachers. It's not often that when we get asked about famous mathematicians, I'm not going to delve too deeply into this now, but there is a kind of a whitening of maths history, and there's most of the major discoveries in maths tend to get attributed to Europeans, and that's not necessarily the case. You can find lots of different examples of contradictory accounts to that, where a lot of maths has been discovered by people from other countries that just didn't get noticed necessarily because it was the European books that were picked up as the mainstream. So this is a great example of a mathematician who I think needs to be more widely known and recognized. So do look into him as well after this. As I say, I'm going to leave it at that for that. So there are other algebraic there's other examples of vocabulary that are a bit odd, linked to algebra. So we have coefficient, bit of a strange word. Factor, another word that, I mean, we do use it in other contexts, but it doesn't necessarily have the same connotations. And I've put linear in here as well, just because I think that's quite an interesting word with links to other similar words with the same roots that you may not have picked up on before. So coefficient just means to bring about a final result. So it's essentially exactly the same word as co-worker. It means the same sort of thing. And factory means to make. So I think I said factory then, but factor means to make, and it is related to the word factory. So if you think about a factory, what does it do? It makes stuff. If you think about factors, what do? They make up, they are the components of something bigger, if you like. So they do share the same sort of root. Linear, I think it'd be no surprise to many of you that linear basically just means a straight line. But it's also linked to some other familiar words that are used in more commonplace words. I mean, line, for example, but also like linen, lingerie as well. These are all related words with the same sort of prefix. Okay, let's move on a little bit. So I'm going to move away from algebra. We will come back to it again in a little while, but we're going to look at what is possibly my favorite word in maths, not because it sounds great, just because the story behind it is utterly bizarre. And this is the word average. Now we've got three types of average that we tend to teach in maths, unless you teach a bit higher up, and then there's another one. But we have sort of mean, median, and mode. Mode is essentially just fashionable, like French. But this word average here is definitely the pick of the bunch. So this is an example of a story that is not, I wouldn't say contested. I think the general consensus is this is the truth, but it's quite hard to get to the bottom of exactly why this word is what it is. But the beginning of that word is from the French avery, which is defined as the portion of the loss borne by each of the many people who invested in the ship. I mean, the fact that we have a word that describes that alone is quite hilarious. How bizarre! Why on earth would that be related? Why would we be using a word like that as a commonplace word within mathematics? Well, the notion really is that people would essentially rent a boat. A group of people would rent a boat and take it out fishing. And it would likely come back damaged, and that damage would have to be paid for. And the way in which the fishermen would pay for that damage is to split the costs between them. So a really odd example of a word that has persisted and come through the ranks to become the word of choice to describe a way of sort of equal sharing. And the AGE at the end is kind of thought to be linked to the English word damage. So they've kind of taken the back end of that word and stuck it on the French word to get this average to infer the damage from the boats. Very odd, very odd. And that's not it. There is another word in mathematics that is boat related. And this one will probably come from left field as well. It's quite a strange thing. Histogram. So histogram, again, strange word. You probably recognize gram as, I don't know if you've thought this through particularly, but gram essentially means to take a record of something, and it's obviously used as a suffix in a lot of words in things like medicine. But histogram, the histos part at the beginning is Greek for the mast of a ship. So we now have 2 words related to ships in maths that you probably didn't know before. And why are they using mast of a ship? Well, histograms in England are very strange things compared to histograms pretty much everywhere else in the world. Generally speaking, people do not mess about with the widths of the bars of a histogram. That's kind of something the English have taken on board themselves and gone, let's just make this even more complicated and obtuse. So if you imagine a histogram without changing all the widths, it's essentially a bar chart. And therefore the rods of the bar chart, if you like, the bars themselves are seen to resemble ship masts. So there you go. God knows why that was the word that went through. I'm sure there's other things they could have thought of, but people settled on that. Just going back briefly to the other types of average, we have median as well. Median just means middle or mediocre, and mean also just means middle. They don't particularly have exciting stories behind them compared to the more general average. All right, so moving on from average, we're skipping B and we're going on to C for calculus. Again, a bit of a peculiar word, which is used in a couple of other fields. It's used in dentistry, calculus, and it's linked to the word calcium. It's got the same prefix for that as well. So calculus, as we know it, doesn't really seem obviously linked to stones and pebbles and so on, but it is. It's directly linked to that in terms of its etymology. If you think about calculus on your teeth, which likely not to be something you may have come across before, but a dentist's terminology for calculus would be little bits of plaque on your teeth, or because they resemble like little stones on your teeth, if you like. And similar, calcium is like it's related because it's like chalky, if you like. So why are we using calculus as a term in mathematics? What do stones have to do with maths? Well, it's a very similar origin story to Abacus, in that when we started formally working with numbers and developing counting systems and so on, a lot of the time it would involve physical objects. There's a classic story of some of the earliest examples of sort of formal counting would be farmers dropping stones into a pot as their sheep went into a field, and then taking the stones out again as the sheep left the field to make sure that they had the same amount that went in as came out. So there is a bit of a history, an ancient history of the use of things like stones and pebbles and sand and so on to do maths. It wasn't pens and paper and protractors and things back then. So there you go. That's calculus, and again, it's linked to these other fields, which you'll see with a couple more examples later on. So I'm going to focus now on some counting words. One is a really odd one for me. It blew my mind. It was just like the most bizarre thing that it just never occurred to me because I don't even think about these things. But one, there's lots of variations of one and derivations from the same sort of root, but things like an just mean one, and a means one as well. It's a derivation of an. And you'll see, even though we pronounce one with a kind of w sound, it's not necessarily always been that way. If you look at the other words that are related to one that have one in them, we don't pronounce the one in them as one. We pronounce it as own. So you can see here we've got atone, we've got non, alone, only, reunion, and I've put condone in there as well, which is the only word in that little list there that's not actually in there. It's a bit of a red herring. So out of those 6 words, the only word there that is not connected to one, even though it looks like it is condone. Condone just means, well, don is from donation. So have a think about it. I'm not going to go through each of these, but can you figure out how each of those 5 words that are related to one, how they're related to 1. You know, why would reunion involve the number 1? Why would alone, maybe that one's more obvious, involve the number 1? And in fact, the most peculiar word that's related to the number 1 is onion. And this is true. It doesn't sound true at all, but it is true. So onion, the on in onion is essentially 1, right? 1 what? Well, if we look at the ion in onion, that's directly related to million, which we'll come across in a moment. So the ion in million means big, and it means big here as well. So onion just means literally the big 1, or a big 1, which is bizarre. It's generally thought, and again, take this with a slight pinch of salt, but it's generally thought that the word originally referred to a large pearl, and then later became, you know, associated with onion because it looks like a pearl. That's one story that is generally agreed upon, but there are a couple of other versions that I'm not going to get into now, but pretty peculiar. So next time you're sat crunching on an onion in the garden, as we all do, that word is related to counting words. Don't worry, I'm not going to go through every number. We could be here quite a while. There's several. There's quite a few of them. But we'll just deal with a few more. We've got 2 here. The W in 2 is silent, but it's not in pretty much every other manifestation of that structure of words. So similar to 1, we don't really pronounce it 1 in any of the other words that it appears in. 2 takes a tw sound where it's used elsewhere. So we have twain, twine, twig, between, as in across 2 things. Twin, kind of self-explanatory. Twice, very self-explanatory. 20 essentially means 2 tens. And twist is the idea of 2 things twisting around, if you can see me. So they're kind of weird. We also have like twilight as well. Lots and lots of different tw words, and the vast majority of them are directly related to the number 2. There are other origin words that mean 2 as well. So we have doubt and dubious. They obviously don't have the tw in them. And duo as well. These all mean 2, but they're from a different root. All right. I'll move a bit faster now. So we've got 4 here. We're going to come back to 4 shortly because of something in algebra. We've got quartet. Quarter just means 1 of 4, obviously. Quarantine is traditionally meant that you would be placed in isolation for 40 days, which is why we've got the qu there. And of course, quadrant as well. 5's a weird one. There's not many words that utilize the 5, but we have fist. Fi is the same prefix, and finger as well, same reason. And we also have punch, which is a bit weird. The drink as well. The drink punch is related to the number 5 because traditionally it used to have 5 ingredients. And whilst punch doesn't have a phi sound in it, it's because it comes from, it's a different language of origin, but it is still meaning 5. You may know this already if you're familiar with my book. I talk about this a little bit in there, but there's 1 or 2 oddities in our language for counting numbers, and that's 11 and 12. If you think about our number system structure, pretty much makes sense all the way through it. The teens are a little bit odd, but even more odd than the teens are 11 and 12. So I just want to quickly go through, explain away why they're odd, and when you chase their origins, they're not that odd after all. So 11, if you follow 11 back to sort of old German, elf in sort of modern day German, but in old German it was ein Lif, which means 10 and 1. And 12 is Wolf now in German, but in old German it was 12, which means 10 and 2. So they do kind of follow the same structure as the rest of our numbers. It's just that some of you may know that the English as a language is essentially a patchwork of lots of different languages, and does borrow quite heavily from German in particular. But don't worry about our number system. While it is a little bit odd, the Chinese do have it slightly easier. Their number system, literally translated, kind of goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 and 1, 10, 2, 10, 3, 10, 4, and so on. So that's a slightly nicer system. But there are far worse systems as well. If you think back to your sort of GCSE French days, you've got like Quatre Vingt Dix and things in French, which you have to. There's lots of different numbers combined to make different numbers. You essentially have to do maths to understand the literal translations of some of the numbers in different languages. Danish as well, I think, has fractions in there as well, just for a bit of a laugh. There are some strange examples of numbers in our language that you might have noticed or not noticed. I think I put one of these in the kind of the summary of the session prior to doing this. So if you look at our months, we've got September, October, November, and December in there, which if you relate to our shape names, our regular gons, you'd be forgiven for thinking September was the 7th month, October was the 8th, November was the 9th, and December was the 10th. And in fact, they were. It used to be that they were they're essentially named after the numbers correctly. It's just that we've added more months in since they were named. So in Roman times, we would have 10 months, and then the Romans added 2 more months in. There was just kind of this lull period between December and March, which was just like winter. And winter could just be as long as you wanted, I suppose. I think it's to do with seasons and so on. But eventually they decided to scrap just this period of winter and put in January and February, so that the calendar just kept on going. And you'll possibly notice as well, we've got July and August, and they are named after Julius Caesar and Augustus Caesar. So when these 2 months were added in, the other ones were pushed back to, but they didn't think to rename them. They just thought, oh, let's mess with people in the future. It'd be hilarious when they've suddenly realized. So they're traditionally named after the numbers, but it doesn't quite work. And March used to be the beginning of the calendar year. And there's also another sort of peculiarity here. Nonagon. So nonagon is peculiar for a couple of reasons, and I'll talk about that a bit more when we look at shapes specifically. But a nonagon has 9 sides, and noon, which has the same root, so it should be linked to 9, is at 12. So what's going on there? Well, noon was originally, similar to the month's story, noon was originally the 9th hour after sunrise. But religion got in the way and it got pushed back a bit, is the easiest way to put it. So again, noon really means something to do with 9, but now it means something to do with 12, a bit counterintuitively. They just keep messing with us, don't they? All right, let's look at the number 100, which again is super weird. So 100, if we split that into 2, we have hund and we have red. And hund means 10 and rad means number. So 100 means 10's number, which is weird, I think. Because to me, when you say 10's number, you're thinking in the 10's column, but apparently not. It's really inferring 10 times 10, 10 tens. Okay, slightly weird. 1,000 gets even more funny. So 1,000, we can split into hund from 100. It's just on the end this time. And thous, which means thick. So we have a thick 100, which I believe in today's youth terms means a fat 100. I don't know. I'm not entirely down with the youth at all. So we have a thick 100 is 1,000. Of course, a thick 100 is 1,000. I mean, surely there's no other more sensible way of naming this number. And meal, we'll come on to meal, I think, in a little bit more detail in a second, but meal means thousand. So million means big thousand. Of course it does. If you think about the length mile, sorry, I just had to move my Zoom picture of me. It's a floating box going all over my slides. Mile, the distance mile, is essentially a mistranslation of meal, M-I-L-L-E, because it used to mean 1,000 paces. It no longer means 1,000 paces, but most of our metric units, most of our units of measure a long time ago were derived from something fairly arbitrary, and there were a lot of problems with trying to translate that across the countries because different countries had derived different versions of things, and it's a lot more scientific now. So mile is no longer 1,000 paces. You know, how long's a pace? It is, I've got it written here, 1,609.344 meters. Feel free to challenge me on that. I think I just got it off Google, which was internationally agreed in 1959. But mile and meal and million, all related. And then going back to 100 briefly, hundredth could also mean 10 12s, which is nice and confusing. So in Old Norse, you know, which we are all fluent in now, it could easily have meant 120 as well as 100. And there's a kind of theory that's not, I don't think it's entirely proven, but again, call me out on it if you can, that that Old Norse would have two bases. They would have base 12 and base 10 systems running at the same time, supposedly. I'm not a historian, so I can't really go into that too much. All right, so we've passed H, now we're at P. Polygon. I think this is most of the time people tend to think this means many sides. Poly, I think most people are happy with as meaning many, and it does, but it doesn't mean many sides. Incidentally, it means many angles. The suffix gon means angle, which I think is on the slide after this one. So we'll come back to that in a second. But we're going to look now over the next couple of slides at the structure of our naming system for shapes, which is again kind of peculiar. Some of it makes sense. You kind of get into the swing of it when you say, okay, we've got pentagon, pent is 5, hexagon, hex is 6, heptagon, hept is 7, enneagon, ennea means 9, and then we go, no, actually it's nonagon. We've decided to change on that one. So most of them follow Greek, but for some reason we decided nonagon, we're going to switch to Latin for a laugh. But then when we talk about 19-sided shapes, we bring ennea back in just because we're annoying. But you think you've got the gist of it, and then you get to 4- and 3-sided shapes, and then we just mess it up all again, and we say, no, we're not having tetragons, we're going to have quadrilaterals, because that's far more catchy. And we're not going to have trigons, we're going to have triangles, because why not? So there's a real lack of convention around 3- and 4-sided shapes. Well, certainly not the same sorts of convention as come in after that. Why is that? Well, it's kind of speculation really, but the general thought is, you know, no one really wrote this down at the time, but the general thinking is that 3- and 4-sided shapes were the things that kind of obsessed mathematicians initially. And we're more likely to be used in things like architecture, and it's only later that we started taking a bit more of an interest in mathematical shapes with more sides, and then that's when we kind of developed these systems. All right, let's move on. So as I said, gon as a suffix means angles. And that makes a bit more sense when you look at words, the other words where gon appears. And most of those other words are in fact mathematical words. So we have here diagonal, and you can see that gon is stuffed in there. And that essentially means across the angles. We also have orthogonal, which means perpendicular to the angle. So it's just like a right angle. We also have other mathematical words that we don't tend to use very much at all. Certainly not in sort of GCSE schooling and things, but we have a digon, which if you think about the naming of the shape system, if you just keep going backwards, you can probably figure out that digon is a two-angled shape, which is a degenerate shape because you can't actually really have one. So if you imagine two dots and join them with a straight line, we can call that a digon if you really want. And then we also have a perigon. Now, when I was writing my book, which is quite a few years ago now, this was the most delightful discovery I made. This is how much of a nerd I am. I was looking at the different types of angles and the different names for angles. So you've got like obtuse angle, reflex angle, acute angle, and so on. Straight line angle, that's a bit of a crap name. Reflex angle, okay, I get it, makes sense. And then the one that was just immensely disappointing to me was full angle. Just the name of it was just a bit crap. So I thought maybe it wasn't always called that. So I went and did some research, and lo and behold, you can call a full angle a perigon. Gon meaning angle, peri meaning full, I guess. And yes, there is a system. This is a very hard to come by resource. I think there's one website on the whole of the net, as far as I can tell, that lists this structure formally. But this is the structure of the naming of regular shapes. So we typically get up to sort of 10, and then we start going, well, I don't really need to know the rest for school, so I kind of give up around there. But you can see here that system continues and can continue forever, really. So if you were desperate to name massive shapes with massive regular shapes with tons and tons of sides, you're lucky people, now you can. So here you can see the general structure. You'll notice that 3 is tri, but we don't say trigon. I'll come back to that shortly. 4 is tetra rather than quad. Then we've got penta, hexa, hepta, octa, nona, or ennea. Ennea is Greek, nona is Latin, I think. And it goes on and on and on and on and on. Now, in real terms, if you're going to describe a shape that's got more than sort of 12-ish sides, then you're probably just going to go, it's a 15 gon, and literally just say the number and gon afterwards. And if you look in a textbook, they almost certainly are just going to write the number and then a dash and then gon. But that's no fun, is it? So let's just be silly for a minute. You'll see in those two little text boxes to the right how we use this table of terms to construct larger, the names of larger shapes. So for example, using these tables, have a quick think and see if you can match up what a 35-sided polygon would be called. I think I keep saying regular shapes. They don't have to be regular shapes. 35-sided polygon. At this point, while I get a chance to breathe, I'll have a quick look in the chat, which might terrify me. I don't know if I can find it. All right, I'm going to move on. 35-sided shape is called a triaconta chi pentagon. Of course it is. And a 672-sided shape, just for a laugh, is called a hexa, hecta, hepta, conta, chi, digon. Brilliant. And if you really want a mouthful, a 999-sided shape is called an Enia Hector, Enia Conta Chi Enia Gon. Now, I doubt that's even going to come up in a pub quiz, so we're reaching new levels of geekery here. But I kind of find it fun, and it's just a bit silly, really, isn't it? Last one before we move on. I think I'll be sharing these slides after this anyway, so usually people try and take a quick picture of this because it's unusual to see all these laid out as this, but you know, I'll just share it freely, don't worry. Here is an octa hecta enia conta chi hexagon. How many sides is it? Oh, I found the chat now. Correct, 896 sides. I'm going to turn that chat off for me. It won't shut it down for you, but it's hugely distracting for me. I'm just like, oh, everyone's talking. Okay, so if you take nothing else away from this, then you can at least go home tonight. Go home tonight. Log off and go and tell your loved ones the names of the most obscure shapes known to man. All right. Keeping on the theme of shapes, let's have a quick look at some other terminology that's a bit peculiar. The radius, that's quite an odd word to use, but when lined up against other things, you can start to see that there is a bit of a theme here. Radius, radio, radioactive. These are all related words with the same prefix. Radius is, if you follow the Latin, it essentially means the spoke of a wheel or a beam of light or a ray, that sort of thing. So when you look at radio, we're thinking like the radio waves essentially, and radioactive, same sort of theme. Incidentally, radius is not a word used in any of Euclid's Elements books. It's not there. He uses the word distantia, which just means distance, which is a bit less specific, I suppose. Okay. Again, looking at common themes across words. Circle, of course, is related to circus and circumstance and circuit. And I'm sure there'll be someone in the comments putting some of the more rude words that begin with circ. Oh, they will now. All of these words are related. Circ is the same prefix for all of them. It's not coincidence. Can you see how a circle, regardless of the word itself, can you see how what it is related to those other three examples? So if we think of a circus is traditionally in a circle. So there's your link there. Circumstance is the events surrounding another event. And a circuit is a ringed connection. I can see someone's put the word that I knew was going to come up in the comments. So circ just means ring. That's what the prefix is. It means ring. All right. Sticking with shapes, let's get to quadrilaterals. As I mentioned before, it's a bit of a peculiar family of shapes in terms of its naming system when you look at the conventions that were in place for shapes after four sides. Quad means four, we've already covered that. But quadrilateral just basically means four sides, okay? Lateral, lateralis, it's all sides basically. And this is super nerdy, but it's weird to me that we've got a family of shapes called quadrilaterals, because when you look at the names of all the other shapes, none of them talk about sides. You know, the other ones we talked about were angles, and and then we go back to angles with triangle. So you'd almost be forgiven for going, okay, if it's quadrilaterals now, then the next one's going to be trilaterals. And you're like, no, it's not that, and it's not trigon either. We're going to go with triangle now. So quadrilateral just means 4 sides. And as I mentioned before, we think that the conventions kicked in afterwards because no one was that bothered about shapes after this. They were too consumed with the 3s and the 4-sided shapes because there's so many different types with amazingly cool properties. And within this family of quadrilaterals, we have lots of different types of shapes with some pretty funny names again. Some of them make a bit more sense, like parallelogram. There's that gram again, meaning something written or recorded. And rectangle, I mean, I confess it was only a couple of years ago where it dawned on me, after studying maths for God knows how long, that rectangle just literally meant rect, right, angle. It's just a right angle. There you go. Mind blown. But some of the other ones are a bit weird, like rhombus. Rhombus is a super weird name for a shape. Kite, not so much. But rhombus is a really strange thing to name a shape. And so we'll link briefly back to the algebra here for a second. Quadratic, quad meaning 4. So why would we call a quadratic something related to 4? Doesn't quite make sense, does it? Maybe it does. So quadratic, it's square essentially. That's where we're going with it. It's referring to the leading term being squared. And if you think about it, the next one would be cubic, which makes more sense. Rather than quadratic. Okay. Here's some more shapes that we're going to get onto. So some of the shape names in the family, in the 4-sided shape family, are named after objects. So it's kind of like sod the conventions. Let's just look at what's over there. Oh, let's call it that. So here's 3 examples of real objects that shapes have been named after. Now, these aren't all 4-sided shapes. These are just examples of names of shapes that are named after objects. So there's a name of a shape that is named after a salt cellar. The shape is not called salt cellar. It's a different language. There's a name of a shape that's named after a table. And there's a name of a shape that's named after a stadium. I'm going to show you those shapes in a second, but what I want you to also do, and if you don't want this spoilt for you, you might want to look away from the chat because I'm sure people will know the answers to some of these. There are several other shapes as well as these 3 that are named after objects. So have a think about whether you know what those are or whether you can think of what they might be. In the meantime, while you're thinking about that, I will, spoiler alert, show you what these 3 shapes are. So one's named after a table, one's named after a stadium, and one's named after a salt cellar. Ta-da! We have the trapezium, which just means table. The stadium, which is just called stadium, which looks like this. This is a popular shape in GCSE maths. It's essentially a rectangle with 2 semicircles on the ends. I know that there's people in the audience thinking he's going to say disco rectangle. Of course I'm going to say disco rectangle. A stadium, that middle shape, can also be called a disco rectangle, which is a mathematically sound piece of terminology. I love it. And the Scalene, that shape on the right, which is a shape made up of 4 circles, I think, 1, 2, 3, 4. Scalene just means salt shape. If we go back, because when we think of salt shakers, you're just like, what? It's not a salt shaker. But that's what we mean, that kind of shape there. If you look at the outskirt of the shape, you can see that it is forming that shape there. 3 more examples here. We have the loon, named after the moon. The oval, named after an egg. And the vesica piscis, I know you all know that shape, which literally translates to fish bladder. Lovely. You may have also put in kite or crescent or lens, which is kind of the other side of the loon. They're all named after objects as well. But we haven't quite finished with the rhombus yet. The flipping rhombus. This is where there's a lot of dispute about why we call a rhombus a rhombus. Now, rhombus, the word, comes from the Greek rhombus, which just means anything that can be twirled. Okay. And the story goes, make sure you've got some salt in between your fingers right now for that pinch. The story goes that there is the rhombus is something that was used in sort of religion, and it's like a spiritual tool, if you like, and people would attach something that was called a rhombus to like a cord, and they'd be swinging it around their head and swinging it around, and it makes a really loud sort of sound. If you want to search for it on YouTube, it's called a bull ringer in more modern terminology. And the Aborigines still use these. So there is video footage on YouTube of people using these kinds of instruments. And the story is that the Greeks in particular, their bull ringers, if you like, were shaped in the same shape as what we call the rhombus. So they called it the rhombus. I suspect some of you out there may have heard other stories, but that is the story that I'm going with because I think it's kind of cool. I can try and find the YouTube link if people can't find it, and I'll post it later. It is quite fun to look at someone doing this kind of thing. All right, moving on. Triangles. I think I'm on 50 minutes, so I need to speed up a little bit maybe. I don't have too much more to go. As I said, triangle, the word is structured a bit weird compared to the other ones, but we've kind of covered that. Let's have a quick look at the different types of triangle and break down why they're called what they're called. So equilateral, I think, is, well, right angled is certainly the most obvious one. Guess why that's called what it is. Equilateral just means equal sides. We've looked at lateral before, from quadrilateral. So the only two weird ones really are scalene and isosceles. Scalene in particular has got a bit of a weird origin. Iso means the same or equal, and scales, S-C-E-L-E-S is from skelos, which means legs. So isosceles just means equal legs. It's got two legs, same length. Scalene's a bit weirder. We have skelenos, which is a really odd word that means stirring up the ground to make it uneven. Okay. So a scalene triangle just means an uneven triangle, but the word, it comes from the word skelenos, which is used more often to describe churning up the ground. All right then. And then we have some descriptions of angles. We have acute, bit of a weird word, and obtuse, which we do use in some other contexts. So acute just means sharp. Okay, so if you think of an acute angle, it looks a bit like a sharp point because you can jab people with it. That's why it's called acute. And obtuse, no surprises, means blunt. And, you know, obtuse tends to mean outside of math now, like slightly odd, but it used to mean slightly sort of thick, I suppose, like a bit of an idiot because you're blunt, you're not, I don't know, very bright, you're dull. Sorry, I'm not trying to insult anyone if people think that when I say you, I mean you. I'll move on. All right. Symbols. So I mentioned 3 books at the beginning. The third book is particularly focused on symbols. It's called Enlightening Symbols, so it's not that surprising. And there's a few symbols whose origins I think are quite interesting. This is not quite etymology, but I feel like I can get away with it. So we're just going to look at a small number of symbols. We have the addition symbol, the equals symbol, and the percentage symbol to start off with. And I've put a couple more in after this. The addition symbol, the plus, is a derivation of et, meaning and, et. So sort of if we were to say 4 plus 3, what we're really saying in old money, if you like, is 4 and 3. And it's just over the years been abbreviated and abbreviated and abbreviated, and now we just use plus as we know it now. The equal sign one of the most fascinating things about that book is when you start to appreciate the relative youngness of symbols in mathematics. Most of them didn't come in until the 16 and 1700s, which is really weird to me, but it's true. So the equals symbol, as we know, it was invented, if that's the right word, by an English mathematician called Robert Recorde. And he sounds a lot like me in some ways. He just got bored and lazy with maths. That bit sounds like me. And he just decided, I can't be asked writing all this stuff about showing things are equal, so I'm just going to invent this symbol and everyone's going to use it from now on. But as we know it now, it's a lot shorter. In the book that he wrote where he first used it, it's really long. It's silly, really. He should have just shortened it straight away. And his justification for using it is that 2 lines of equal, something about 2 lines, nothing can be more equal than 2 parallel lines or something. I'm not sure his justification was very sound, but whatever. And the percentage symbol is a bit similar to the addition symbol in that it's abbreviation of a word over time has just become used as a symbol. Or at least that's the story that I've read over a few sources. So the story is that percent, which means percent out of 100, in Italian is percento, and that would commonly be abbreviated to a P and a slash and a C. And over time, that essentially, to shorten the story, just manifested itself into the symbol that we see today. So the symbol that you can see for percent really is kind of a P slash C, or so the story goes. And again, this is just because I was browsing the book and thought that these are really interesting little geeky facts. The reason we use lowercase in algebra and not uppercase is again an Englishman, Thomas Harriot, who in the 1500s was a mathematician, wrote lots of books. He just decided this was going to be his convention. He was like, right, I'm going to do lowercase. We should all do lowercase. And it didn't really get picked up by many people. And then Descartes did it afterwards, claims that of course he didn't see it in Thomas Harriot's book, it's just his book. And Descartes' book, I imagine, was a lot more popular and more influential, and it took off from his book essentially. But Thomas Harriot was the first one to do it. If you haven't heard of Thomas Harriot, do look him up, because he's a British mathematician, so that's great. You can get a bit of nice English history in there or whatever, or British history in there. But he's also more well known for being the mathematician who, this is so bizarre, who set polynomials to 0. So if you think of the traditional way in which we deal with polynomials, where you go, right, get it all to equal 0, that was his thing. So go look at that, it's quite interesting. And subscripts as well, for like squared, that was Descartes as well. So you used to just, I mean, there were lots of different ways people would write something to mean something times itself, or times itself, times itself, times itself, and so on. And what typically would happen is at the front end of the book, people will go, right, I'm going to do it this way, and now you know how it's done. Descartes said, right, what I'm going to do is just put a little 2 at the top, and that means x times x, or a 3 at the top, and guess what that means? And it really took off from there. So I kind of like that as well. And finally, on this section, I really am running out of time now. The A to Z thing, I'll mention this super quick. Around that same time, I think it may have even been Descartes himself, but I'm happy to be corrected. The convention was developed that you save anything from P down to Z for variables and use A onwards for constants for algebra. This is out of that book. It's wonderful. I'm not going to go through it now because I'm running out of time, but you'll have the slides. This is a brief history of mathematical notation, when it was introduced and who by. What a brilliant little resource that is. Okay, finally, I'm going to race through these because I think people will know some of them. Anyway, some fantastic mistranslations in maths. We have The Witch of Agnesi, which is not in the GCSE curriculum. But this term witch is really odd, and it shouldn't be called witch at all. It was a mistranslation from, I've got it written down here, versed sine curve, which is written as avericera, to the Latin vertere, which means, to something else that's spelled almost exactly the same, but with two V's, which means wife of the devil, and was translated by a mathematician in Cambridge, and it stuck. You'd think they'd just correct themselves, but no, it stuck. Surd is quite a common story now. Surd is a really odd word. It means deaf, and it's a combination of a number of different mistranslations and misinterpretations. Originally in Greek, it was called alogos, which means not rational, and that was translated into deaf because it sounds similar to another word and then translated back and so on. It just gets very silly. It should just be called irrational, but we call it surd.
Oh yeah, last 30 seconds.
Yeah, last one is sine. There's 1,000,001 stories about how sine got mistranslated. Some all slightly different from each other, but essentially sine has been translated from curve to curve in a toga, which essentially is emphasizing that you're talking about someone's bosom. Whoops-a-daisy. Very finally, zero, because I need to get to Z, comes from sifa, which is Arabic for empty, which is also related to the word cipher. And I think I'm going to stop there. Thank you very much. I'm sorry I've just kind of super raced through the end, but I'm conscious of time. I hope you've enjoyed it and learnt something.